Okay. Right, guys. So today we'll be continuing to discuss on the previous lecture slides, which is on counter and also shift register, right? So if you guys see on this slide, so this is regarding the counter circuit that we have discussed in the previous week. So if you guys still remember, we are using the clock, right, to to develop our own counter. So for an example here, let's say, like we give the amount of the counter that we want. So it begins with n. So where does this n come from? So look into the code here. So the n comes from the input itself, right? So the user is inputting the value, the n number here. So this is the counter. So it's gonna count based on the n value that the user set. All right. So for an example here, right, n. So how many count can you do, right? So check here. So n bit, the size is 16, right? So 16 minus 1 is 15 to 0, which means 16 bit. And if you can check, right? So the value, what's the maximum value that you can go with 16-bit numbers, right? So this is just the calculator that you can find from your Windows OS, right? So you can type 111 for 16 times, right? Which means it is 16 bits, right? So just convert it into decimal here. You can see it. So in decimal, you can count up until 65,535, right? So this is the maximum number of counter that you guys can develop. So let's say you insert 111, right? So and then the counter will start from 65,535, right? But wait, is it 65,535? But actually, wait, yeah, yeah. So it's gonna be so it starts 65,535, then it's gonna reduce one value at a time until it reaches 0, right? Then the tick will go high again. So you are counting. So every 65,535 clock cycle, then you're gonna the tick gonna be high for just one period of time. Let's see here. And right, so this is your clock, right? So log in. Oops. Yeah. Yeah, it's like that. Yeah. So this is your clock. So after 65,000, right? 535 clocks, you count one by one, 1, 2, 3, and then you're gonna reach until 0. Then the tick gonna go high again, right? So how you determine when the tick is gonna go high? So it's depend on the code here. So if you see here, after the user insert the n value, right, then it goes into this always loop, right? So always condition. So always at positive edge of the clock in, right? So based on the clock in, and then if enable is equal to 1, and then check again. So if the enable is equal to 1, if count equal to 0, begin, right? Begin, tick equal to 1. So tick equal to 1 here. And then count equal to n. So if you set n is equal to 65, 535, equals 111, right? 65, 5, 3, 5. And then begin. So for the next clock cycle, at the second positive edge, right? So at the second, so at the second positive edge here, so this is the first positive edge, which gonna execute this part. So at the second positive edge, you're gonna check again. Enable is equal to 1. If enable is equal to 1, then check. If count equal to 0, But right now, count is not equal to 0, right? Because you already assign count to 65,535. So you're going to go into the second part of the code. So then tick equal to bit 0. So that's why you see here tick goes down 0. And then count start to decrease. It's going to decrease up until the count value will become 0 again. Will become 0 again. Then the tick gonna go high again, right? So that's about the clock tick. So if you guys have any questions, can let me know, right? Okay, now, okay, then the second thing that I want to let you guys know, is, the timing, if you want to consider, right, the timing here. So how many seconds that you want to make this tick occur, right? So the repetition, you want to set it, and let's say like how many seconds. So it's depend on the clock that you use, right? So for an example, if you guys are using 50 megahertz clock, so what does it mean by 50 megahertz clock? 50 megahertz clock means that, let's say this is your clock cycle, right? Okay, this is considered as one complete cycle here. Right, so this is one complete cycle. One complete cycle. Right, so if 50 megahertz means that mega is equal to million, right? So that means within 1 second, within 1 second of time, there is 50 million. 1, 2, 3, 1, 2, 3 cycles. Right, so this is what it means by 50 megahertz. So if you guys want to know the clock cycle for your PC, look at the frequency. So I think most of the PC right now is around 2 to 3 gig, right? Gigahertz, right? So you convert it. So that means that's the number of cycles within 1 second that your computer operate at, right? So for an example, this one, the circuit, if you're using 50 megahertz, that means within 1 second, there is 50 million cycles. So if you guys want to know, one period of 50 megahertz here consists of how many seconds, we just divide it. 1 over f, right? So T is equal to 1 over f frequency. So you will get one complete cycle here is equal to 20 nanosecond. Right, so this is something that even human eyes cannot notice, right? If there's a changes at every 20 nanosecond, even human eyes cannot notice the changes, right? So this is considered as fast. But right now the computer is working at the faster rate than this, which is around 2 to 3 gigahertz, right? So the changes of the circuit within, so if you're using 50 megahertz happening at this rate, so if your PC, right, so they are happening at 2 to 3 gigahertz rate. That's why if you see in the phone, right, I think the range is around 1.2, right? 1 point something to 2 gigahertz. So what happened is that, so when the changes is too fast, what happened? So all the electronic, the digital circuits, right, changing at a very fast rate, so it create heat, right? So that's why sometimes your phone, right, when you use it at full capability, you utilize most part of the circuit, then your phone or your smartphone will become hot. So same goes as your PC, right? So as your PC is processing high load, then you're gonna hear the fan in your laptop turn on. If you're using PC, of course, it's gonna turn on all the time, right? So, but if you're using laptop, then if they are not really like having a lot of heat in the laptop, so they're not gonna turn on the fan, right? But it's tremendous amount of heat being produced from the processors. Yeah, then you're gonna turn on the fan. All right, so there's just additional fact so that you guys are getting more interested, to learn about digital electronics, which I think is fundamental things that you guys have to master. All right. Okay. Now we go into cascading counters. All right. So this is kind of interesting, right? Okay. So when we talk about cascading counters, right? So here in this example, they want to create a tick here that happen every 1 millisecond. All right. So here's the counter. I mean, here's the clock tick. All right. So how is this happening? All right. Same goes. So clock tick, you can refer into the previous slide, right? So the tick here gonna happen every 50,000, right? So but you have to set it from 49,999 because it's gonna go from 49,999 until zero, right? Which in total will becomes 50,000. All right, so every 50,000 of the tick here, then you're gonna increase the value here. So if you can see here, I mean, they give you the value 1 millisecond, right? So 1 millisecond. So how did they got into this? Okay, so how we can do this, right? So how we gonna verify that this value is correct, right? Okay, first, like I've told before, right? So look at this value. So this is 50 megahertz. 50 megahertz. One, two, three. And then here is 50,000. Right. So let's make the 1,000 first. Then 50. Right. Then you divide it. So you divide it. So you just cancel the common one. Right. Then 5 you divide by 5 becomes 10,000. Right. So then here you mean what is left is that 10. Is it? Yeah. It's 1,000. Right. So it's 1,000. Is it correct? 1, 2, 3. Yep. Yep. So what is left is just 1,000 cycles. Okay. Then I've told you before. Uh, 20. Mean for 50 megahertz clock, one cycle is equal to one complete cycle, which is 1 over 50 megahertz, is equal to 0.2 nanoseconds. Okay. All right. Okay. Wait. I'm getting confused. Okay. Wait. I've done the calculation before, but let me refresh my mind. So 0.2 nanosecond. We should just nanosecond times it here. All right. So nanosecond, 0.2 nanosecond. All right. So we times it by 1,000. So what do we get? So we get around 200 nanosecond, which is equal to 1, 2, 3, 0.2 millisecond. Okay, wait, how did I get into 1 millisecond? Okay, wait, sorry guys, I'm confusing you guys. So let me check. Wait, all right. So this is 50,000, and then divide by 50 million, right? 50 megahertz. Then we divide by 50,000. 50,000. Oh, no, no, no. Okay, sorry. Okay, let's do this again. All right, so let's reset our mind. Okay, let's do this again. All right, okay. All right, sorry guys. Okay, 50,000 cycles, right? So 50,000, because this is 49,999 until zero, which will become 50,000. So we times it by 20 nanosecond. Simple as that, right? So 20 nanosecond is what we get. All right, so let's just have a calculator here. Nanosecond standard, right? So 20 nanosecond is equal to what? All right, so 20 nanosecond is equal to 1, 2, 3, right? And then 1, 2, 3, 1, 2, 3. So how many nines you have here? So one is how many 0? 1, 2, 3, 4, 5, 6, 7. All right, okay, let's do it. Okay, 0.1234567 times by 50. 1, 2, 3. So you get, okay, right. Okay, so you get here 0.01, which is equal to 1 millisecond, right? Okay, sorry guys, just make you guys confused. So how we count it? So we just get the total number here, which inserted by the user. So in this case, they insert 49999, right? So which is equal to 50,000 cycles. Then you just times it with the what do you call it? The period of the frequency, which is 1 over f. You get 20 nanosecond. So 20 nanoseconds, you times it by 50,000. Then what you get is equal to 1 millisecond, right? So that's why here. So, I mean, you guys can figure out, right? I mean, so if you guys want to make it count every 2 milliseconds, what's the value that you should give here? Answer it in the chat box, right? Or you can say, so 50,000 is generating the counter every 1 millisecond. What if you want to generate a counter every 2 milliseconds? Okay, correct, right? So you just double it up, right? So you double it up, so it becomes 100. But here, if you see me like 100, 100,000, so you don't set it as 100,000, right? You have to set it as 99,999. But then you have to check whether 16 bits can occupy the number up until 100,000. So you can check it. Just go and do the calculator part. Right, so programmer, and then okay, decimal 999.99, right? Okay, see, is it enough for 16 bits? No. Right, so how many bits we need to have? So we need to have if you can add 17 bits, right? So you can see here 4, 8, 12, 16, and here 1 here. So 17 bits, right? So the size is not enough here. So you have to change the size too. So I mean, this is just example, right? So maybe in the exam it can come question like this, right? So I mean, if you want to set the tick, the counter every 3 milliseconds, right? So we modify the circuit. So make sure you guys understand this part of the calculation. All right, so again, this is the clock divider. So how you guys can divide the clock? So it's still the same, right? So let's say you guys are giving 50,000, same like this before, 49999, right? So, I mean, what's the clock output that you can construct here, right? So, I mean, this is how you want to divide the clock. Clock divider means that, right? So, instead of, let's say, you have 50 megahertz input, right? But for certain part of the circuit, you don't want it to change every 50 megahertz because, or every 20 nanosecond. So you want to make it a little bit slower. Right, so how you can do this? So we are using the clock divider. So let's take an example here, right? So I mean the circuit, I think it's almost the same. You can look later. I'm going to describe the coding. Right, first we understand the concept first, right? Okay, let's say we want to make the output clock slower a bit, right? So let's say we are giving the same number here, 4999, which means it's equal to 50,000, right? So what happened is that, so again, we do 50 million, right, which is 50 megahertz. So we divide it by 50,000. Now we divide it. Okay, I got confused with this calculation before, right? So you divide it. So what you get here is equal to 1,000. So 1,000 is equal to what? So this is your 1,000 hertz. So if you want to slow the clock down to 1 kilohertz, right? So 1 kilohertz, what you need to do is that you give 50,000 input here at the K. So which is 49,999, because it goes up until 0. So this is also equivalent to 50,000. 50,000. So that's why when you just divide it. So 50,000 cycles, we divide it with, 50 million cycles, we divide it with 50,000 cycles. So what you get is 1,000, right? So you divide it, so you get 1,000. So that means the output, it's not one, it's not, okay, 1,000 cycle is just creating this high here. So here, I mean, it gonna take like 50,000 cycles to make it high. So but then one complete cycle, right? So one complete cycle has to goes up and then down and then go up again. So it's gonna go low again. So by using this code, right, another 50,000. Okay, so so this calculation is wrong. Wrong again. I'm not sure what's wrong today. Okay, right. So erase this time. Okay, okay. Let's say we give here 50,000. I think to make it easier, right? So 50K. Alright, so it's gonna go up for 50,000 cycles, and then it's gonna go down again for another. This is how we want to count the output clock, right? So 50,000. All right, so we divide it. So 50 plus 50 equal to 100. 100,000 cycles. So 50 million, 1, 2, 3, 1, 2, 3, you divide it by 100K cycles, right? So cancel this part. 1, 1. So you got 100 hertz. So the output here, so you insert 50 megahertz clock, right? So the clock in is 50 megahertz. So the output is equal to 100 hertz. So how do you get 100 hertz from this calculation? Right, so you count 50,000. So based on the code, right? You see here, so the code going to go high for starting from your counter. Right, let's say yours is 499, right? So it goes until 0, which is in total 50,000. It's going to go high. Then after that, it's going to go down. Then it's going to stay down for another 50,000 cycle. So in total, one complete cycle is going to take 100,000 cycles. Takes from this clock, right? So then 100,000 cycle, you divide it by 50 million. Then how you get 100 hertz. So this is your output. So this is how you implement a clock divider. Right. Okay. All right. Okay, guys, if you guys have any question, please let me know, okay? All right. Okay, so this is how the code's functioning. All right, so same. The K, the value, input value will come from the user. Right, so this is like I mentioned before, just make life easier as a programmer. Right, so if any changes that you want to make, just change at this part. You don't have to change at the whole part of the code. Right, so and then here at the bottom, then you initialize the output to become 0 first, right? So at a positive edge of the clock, then you check if enable is equal to 1. So this counter will just operate when the enable is equal to 1. Right, so if count is equal to 0, then you just invert, right? So clock out, invert the value of the previous clock out. So if it's 1, then it becomes 0. So if it's 0, then it becomes 1. And then count is equal to K. So that's why you see here, the initial value is equal to 0. Then when at the first clock cycle, here, at the first clock cycle, it's going to check here, right? So if the count value is 0, yes, the count value is equal to 0, then just invert. So now clock out becomes 1 high, right? Invert. So this is just invert. Right? Okay, K bit refers to. Okay, K bit here is variable. Here is the K bit. So K bit here is just like the variable, right? So variables in programming. Right, so you say A is equal to 3. Right, so at the bottom here, you just call A plus B, right? C is equal to A plus B. So anytime you want to change the value of A here, so if they say, let's say like there's a 100 of coding, right? 100 lines of coding that using A. So if you want to change A value, so you just change at this part here. So erase it, change it into whatever value that you want. Let's say 5 or whatever. So you don't have to go line by line to change it, right? So this is just a coding technique. So K-bit, you assign it as 16 value, right? So it's gonna, you just call the name here. So K-bit. So K-bit is depend on whatever value that you assign it. So in this case 16, so it's 16. So 16 minus 1, so this value is equal to 15. So in future, let's say you want to change it, so just change it. So you want to change 8 bit, right? So if you change 8 bit, then it becomes 8 minus 1, 7 to 0. Right? So just like that. All right. Okay, then invert, okay, then assign K value to count. So in this case, we assign the K value is equal to 4, 9, 9, 9, 9. So it's going to be assigned to count. Right, then at the second positive cycle here, it's gonna check, right? Enable is equal to 1, yes. So if count equal to 0, no. Count is not equal to 0 because we already assigned count to this value. Then go to the second one. Count minus 1. So it's gonna minus 1 from here. Until it becomes 0, then it's gonna go into this condition, then invert the clock. So that's why when it reach here, 0, then going to invert the clock from 1 to 0. Okay. Shift register. Okay, so we're done with the clock. Now we are going into shift register. For shift register, all right, so as we understand that you're going to shift the input, right, one at a time. So at first clock cycle, the one value is here, and D. And then second clock cycle, then one value gonna move here. Right, then one is here, then it move to the next one, right? And I mean, this is just the basic concepts, right, for how we can use shift register as the control. Right? So in this topic, right, we are discussing about control. Right now we are looking into how we can use shift register as a control. I think this slide is kind of, will make you confused. So I think let's use in this slide, right? Okay, now before we go into how to make shift register as a control circuit, we try to understand first how this shift register function. I think most of you guys have go through this. I'm hoping that you guys understand the circuit, so that don't get confused when you look at this coding. So there are many way of doing the the shifting code, Verilog code. So this is one of the method that we can use for the shifting code. But I think that there's a specific command that you can use for shifting, right? So like this command, right? Shift left or shift right. So shift right is the other way around. But in this case, we are not using this signal, this what do you call it, symbol, so that we can have better understanding how it is shifting. All right, okay, oops. Okay, now let's look into the example here. So we are using a multiple flip-flop here, right? So I mean we connect the flip-flop in cascade, right? So cascade or in series, right? So there are 4 flip-flops involving here. I mean you guys have to understand and know how the circuitry looks like, and know how the connections, right? So because I mean like we can ask anything in the exam, right? So just prepare for any possible question, right? So the clock will be connected to the same clock source, right? So that all the changes will occur at the same time based on the clock. So when there's a clock connected, so we know that this circuit is synchronous circuit, because the changes of the circuit is depend on the clock changes, right? So we input the data, right? So data in here from 1D, then at the first clock cycle, I mean it's gonna go into S register 1. So that's why we can see here. So input is data in, which is only 1 bit, and output is data out, only 1 bit. And then input clock, right? So register 4 to 1 SREG. So I mean, like I said here, so you can see 1 to 4 because they just do this to make it easier for us to understand. So you can also do 3 to 0, which is also the same, right? But to make the numbering clear, so that's why they use from 4 to 1, which is also same. This is a 4-bit register, and then the name is SREG. And then initialize the value. SREG is equal to 4-bit, and all of the bits are 0, and then always positive edge of the clock, right? So begin, right? So begin. What's happening here? So what's happening here is that I mean like all the code will be what do you call it, execute here. So this is going to be done in parallel, right? So what happened is that, so the data in, so let's say we insert the data value A, right? So I mean it can be bit 1 or bit 0, right? So at the first clock cycle, A will go here, right? So but at the same time, the value here is 0, right? So A move here, so we insert A. So by default, this is 0, right? So A gonna go here after the first clock cycle. So by default is 0, then 0 gonna move here, 0, 0, 0. Right, so A now is in SREG 1. That is the first clock cycle. Right, at the first clock cycle. And then at the second clock cycle, what happened? So now A is in here. Let's say now we change the value. So now data in is equal to 0. Right, so now at the second clock cycle, A will go into SREG 2. A will go here. A. And then we change to 0, right? So second one 0. then 0 gonna go here, 0, and then again 0 gonna go there, 0, and then 0. So that's how it is up until A reach S rec 4. Then you're gonna see the output data out here. So that's what it meant by shift. Yeah, it's gonna shift one bit at a time. So every clock cycle is gonna shift one bit, move here, and then second clock cycle move to 2, third clock cycle move to 3, and then the fourth clock cycle move to 4. Right, so there's a shift register. Okay, so this is the example, right? So this one we call it as linear feedback shift register. So when we say linear, to understand when we say linear, there must be a pattern. Right? So let's say whatever it is like this, and then it's gonna repeat again. Right? It's gonna repeat again. Pattern. Right? So when it's a linear, there must be a pattern. So this is almost similar like in trading, right? I'm not sure how many of you have started to trade stock or whatever, forex or whatsoever, right? So pattern is the thing that we have to master, right, in those stock trading, so that we know, I mean what's the trending, right? The trends is showing based on the pattern, right? Okay, now forget about the stocks. Okay, let's go back into digital electronics too. Right, so this is LFSR. So as we can see here, how we can use the shift register as a control circuit. All right, so as we can see here, when we insert one value, right, so we just insert one value here. So at the first clock cycle, then the 1 will go into Q1 here. So we can see the Q1 at Q1, 1. And then Q2, Q3, Q4 is equal to 0. So this is equal to 1 in decimal, right? 0001 is equal to 1. And then we shift it. Next clock cycle, we shift 1. Right? So we shift 1. So look here, right? So there's XOR here. Then we're gonna see how the loop back will happen. Right? So then for the second clock cycle, 1 will go here. Right? And then 1 will go here. Right? So the total output in decimal is 2. Right? 0, 0, 1, 0. And then in next clock cycle, then 1 will go into Q3, right? 1, it becomes 0, 1, 0, 0. Okay, now we have input here 1. 1 here, and then 0 here. Right? So for XOR, I think XOR, so when it is 0, 1, okay, when it is not similar, right? So here is 1, here is 0, so the output here will becomes 1. So that's why when we see at the next clock cycle, what happened is that 1 value goes in. So that's why we see here 1 goes in, because the result of the XOR, right? So this is the XOR result, right? It is XOR between Q3 and Q4, right? So 1, 0, then the output will becomes 1. Then gonna feed back into this shift register circuit, right? Then it's constructed 1, 0, 0, 1, and in binary, in decimal, it becomes 9. All right, so you can follow the truth table and check how it works, right? So you can see all the numbers 1, 2, 4, 9, and then 10, 5, right? So you keep on changing until here. So when it reach here, so you can see it's going to repeat the pattern again, right? So this pattern will repeat multiple times, and as long as you don't keep on feeding back the input from the XOR. Right, so from this circuit, we can see here, there are many states that we can use, right? So 1, 2, 4, so these are all different states. So we haven't go into the state diagram part yet. Wait. All right, so 1, 2, 4, 9. Right? So these are all state. 1, 2, 4, 9. Right? So it's the same like counter. Right? It's going to go into different. So you can set, right? So let's say 2 here is what? I mean, like using the example of washing machine again. So let's say like 1 is inserting the clothes, right? So insert the clothes. So insert the clothes, I think there's not much control signal that you have to control. Right, so second, insert water, right? So when after you already put the detergent, the softener, then you close it, then it's going to start to pump in the water. So you have to send the signal, right? Send the signal to accept the water flow, accept water flow, right? So water flow. And then second after, I mean, the water has reached the certain level, then stop, right? So this is your control signal. Stop the water flow. And then what? Start spinning. How long you want to spin? Start the counter. Start counter, right? Counter. So how many count you want to do? It depends on you. Let's say 10 minutes, right? 10 minutes, right? So count. So until it reach, then it goes into another cycle. So this is how you can use the shift register as a control signal. All right, so we finished that part. Any question on counter and shift register? Now we go into a new slide for today. Got any question, guys, before we move into this new chapter? All right, so if not, then I think we can just go into this new chapter. All right, so now it's a marks-based transfer. All right, okay, guys. I mean, just remember again, right? So now we want to develop an electronic circuit, right? So electronic circuit. So when we want to develop electronic circuit, so one of the most important thing is register. All right, so okay, let's take example of your, let's make this like recording. All right. Okay, let's say we are doing the ALU, right? So this is your ALU circuit, arithmetic logic unit. All right, so this is your input A, and this is your input B. Let's say you want to process a lot of number, right? So you have to store the number. Okay, let's say there are 7 numbers. Right, C, D, E, F, G, H, and I. 1, 2, 3, 4, 5, 6, 7. So let's say there are 7 numbers that you guys need to process. So you have to store all the numbers first, right? So that you make your processing faster, because you don't want to keep waiting for the user to input one number at a time, right? So we want them to just, pump in the number, and then so that we can store it, and then we can execute it as fast as possible. So what happened is that then we need a register. Remember, right? I think register, I covered it in the first lecture, and the first online lecture that I've shared with you guys. It's not really like on the week 1, so I did it earlier, and you guys can refer to it again if you guys haven't got any idea on what is register, right? So by the way, it's just a temporary memory, right? Temporary memory where you can store data. Okay, so here you store C, and then D, right? So you can have it until I. So in this case here, you have 7 different register, right? So 7 different register, and then you have to connect all these register to these 2 input. So how you going to do that, right? So that you can select it easier. So which one you're going to fit into A, which one you're going to fit it into B, right? So that's why here in this case, we need to use marks, right? So we have marks. So all of this input going to be connected to both marks. And then it's going to go into A and B. Then we choose here. So there's a selection here, right? So it's depend on how many bits that we need to use. So in this case, if you have 7 bits, we at least minimum we need to use is 3 bits, right? So we can use select to choose which data that we're going to fit into A. Right, then here we have another one, which is our result. Right, so to develop a circuit, so we have to have a using a storage here, right? And then here all the connection here, we call it as a bus. Don't just get confused on bus, right? So what is the purpose of bus? Purpose of bus is to bring people from destination A to destination destination A to destination B. So that's purpose of bus. So here bus is taking the data from different register to another register to be executed somewhere, right? So in this case is to be executed on ALU. All right. Okay, so this is an example of dedicated marks-based transfer. So, as you guys can see here, so each register will have one dedicated marks. So, why is this connected like this? So, this is make our life easier in the circuitry, in the circuit. If you want to move around the data, right? So, let's say you want to transfer from data from register 0 to register 1. So how are you going to do that? Right, so by using mark. So that's why the output from R0 is being connected to all other marks. Right, so marks 1 and also marks 2. So let's say you want to transfer from R0 to R2. Right, first what you need to do is that you just choose the select for marks, marks 2, right? So see here, where's the output from R0? Just follow the line, and then you can see it goes into selection 0. So here's a 2-bit selection. So you just choose 0, and then it's going to feed data from R0. We go into R2. Same goes if you want to move around. Let's say you want to move R2 to R1. So you just follow the line, R2 goes to R1, so it's a line 1. So you have to send one value here. So you're going to select from input 1, then the value from R2 will goes into R1. Alright, so that is dedicated marks-based transfer. If you guys don't understand or cannot follow me, just let me know, right? Okay, because I'm just talking to my laptop here. So if you guys don't understand or whatever, need me to re-explain it, then just let me know. Okay, let's go to the next slide. Oops, okay, yeah, this is just an example of the line. Okay, again, yeah, I think this is just the same example, dedicated marks. So this is just in terms of the signal, right? So how it moves around. So the advantage, right? So the advantage of using these marks, you can, the advantage of having these settings, you can move data simultaneously. And for an example, right? So you want to store data from R0 to R1, right? And then at the same time, you want to move the data from R2 to, but this is let's say we have 4 register here. So let's say there's R0, R1, R2, and then R3, right? So at the simultaneously, you can move data from R0 to R1 and then also R2 to R3. Right, so I think that is the only main advantage of having this kind of circuitry. We're gonna look into alternative, right? Because this is not our preference technique to develop the bus or the connection. Why? Because they are using too much logic circuit. You can see here, I mean, they need up until 3 muxes, right? Which is gonna consume a lot of logics. In idea of designing a circuit, right? So we will try to minimize the number of digital logic gates that we want to use, because we want to reduce the number of the circuits. As you reduce the number of the circuit, the size will be smaller and the cost will be lower. Right, so that's the idea in design. That's why if you see, you know, I mean, like when it wants to go into product, right, people, the most thing that concerning people is the cost. So if you have a great product but the cost is too expensive, then not many people are gonna buy it. But if you have a good product and the price is reasonable, then a lot of people are gonna buy it. Right, so that's the idea in designing. Okay, next. I think this is just most easier. You guys can refer to the slide. All right, okay. This is the same example. All right, so one of the other alternative, right? So one of the other alternative, instead of using the previous design, right? So what we can do is that we combine all the register into one mux. So as you can see here, we reduce the number of mux that we use. For an example, instead of using 3 muxes, right? 3 different muxes here. So we just use 1 mux, but the input is from 3 to 1. So this is 3 to 1 mux. All right, so of course the obvious disadvantage of this design is that you cannot do the simultaneous transfer. So only one transfer can happen at a time, right? So either from R0 to R1 or R0 to R2, or any of the possibility of the connection here, R1 to R0, R1 to R2, or R2 to R0, or R2 to R1. All right, so what else? There's multiplexer bus. Yeah, this is just showing you guys the example, right? How you can choose the select, right? Okay, for an example, if you want to move, let's say 00, you want to move from R0 to R1, right? So R0 to R1. So you just select here. So this is 0, 1, 2, 3. So in this case, you want to select R0, so it is 0, 0. So you're gonna go take from R0. Right, so whatever value, let's say value inside here is 7, then it's gonna go into the bus here, right? So but then, so the bus will go into whichever register that have the high load signal. So the data will be available on this line here, on the bus here, but it will go inside the register that the load signal is being activated, right? So for example, you want to transfer from R0 to R1, then you have to send high signal here. 1 send to R1, then 7 will go into here. Right, so here is only ins. Okay, let's say you want to transfer from R1 to R2, same goes. So from R1, so let's say the value is 5, so R1, then you have to choose 1 here, right? So that means select is equal to 0, 1. And then the data of 5 will be available on all the bus, but you want to transfer it to R2. Then you have to send high signal to L2, right? So it's going to go travel here, activate, then 5 will go into R2. So that's how it is for the data transfer. Okay, this is another example, right? Same example. Multiplexer bus, same. Okay, this is another type of bus, right? So this is just a comparison. So mux base, which is dedicated mux base, and bus base. Bus base, right? So bus base can be done into 2 forms. One is by using the mux. So mux here, right? So one mux connecting all register. And then the other one is we can also remove the mux. So we remove the mux here, but then all the, what they call it, all the load will be, sorry, not the load, all the register will be connected to each other. Right, so normally I think modern design, right, so they're using here the 3-state bus, right? So I think this has the advantage of the most efficient design, and because they're using the less circuit or less number of gates compared to the mux design. So what happened is that, so you can connect or you can transfer one data at a time, same like mux, right? So for example, if you want to move the data, right, from load R1, so you have to activate the gates here so that the data will be released. So let's say you want to transfer from R1, because this bus here only can be used as and only can be used by one register at a time, right? So one user at a time using this bus. So let's say R1 want to transfer to R0, so only R1 can use the bus, right? So all of the rest of the register R2 and R0 has to lock down their input, so the output cannot go out here. So it just got stuck here. So but for R1 it can pass here. Then let's say you want to transfer to R0, then you're going to go here and then go into load. Plus you have to send the load signal to rest so that the data will be stored. So let's say you want to transfer number 3, and then it's going to go into 0. So one user at a time. Then if another register want to use the bus, so R1 has to stop, block it, then R2 can start to use the bus, right? Right. So basically, I think that is about the bus. So you guys can have the can look at the difference of the design, right? So it's using multiplexer, and here it's using the without a multiplexer bus, right? So but most of the cases going to use this type of bus because it is faster. Why it is faster? Because you don't have to go through the signal, you don't have to go through many logics. So when we have mux here, we have additional logics, right? Of course, additional logic will cause delay, right? And also, additional logics is also not preferred because of the cost, right? So normally we go into this. All right, so in your design later, if you need to use this kind of bus, right? So maybe for the ease of design, maybe you don't have to use this kind of bus, right? So you can use the mux type of bus for you guys to make the data transfer easier. So the more elements that you use for your mini project that you take from the lecture content, right, the better marks that you will get for your mini project. All right, so I think that's all for today's lecture. Right, so before we end the session, do you guys have any question or anything that you want to get? When we minimize the circuit, so the coding will become long. Minimize the circuit, the coding will become long because okay, this is okay. So I think to rephrase your question, does the coding has direct connections with the size of the circuit? Not really, not really. I think is depends. So the coding is one part, right? Coding is for the developer, the language that we understand, right? So we can use many type of codings, and then the number of the circuit is depend on the software, the optimizer, right? So when they convert our code, right, our coding into circuit, right? So then that's the important factor. How powerful the tools in reducing the number of gates that they can use to construct the circuit that we want, right? Because we are coding the logic, right? But the circuit implementation will be done by the software, right? So when we minimize the circuits, so the coding will become no. So I think not really, right? So it's kind of abstract question, right? So because some of the coding, for an example, right, for shifting coding, right? So you can you can use for example, right, for shifting coding here. Right, so you can use this kind of coding, and also you can use a lesser coding, right? By just using the symbol. So you don't have to describe something like this. Right, so your code becomes lesser, but the circuit is the same, right? Yeah. So I think I hope you guys get the picture. How's the connection between the coding and also the circuit? Right, circuit is different thing. Coding is different thing. Coding is the language that human understand. Right. For example, we understand this part. Right? We can translate it. But when they got into the software, when they compile it, they change into the circuit. So it's gonna construct a circuit like this, for example, shifter. So same, if you don't want to use this kind of coding, so you just use the symbol, right? So the symbol, right, of the shifter, shift left or shift right. You don't have to construct all these things, but still you are implementing shift register. So same circuit, different coding. All right. So that's kind of tricky question. All right. So any other question?